start maybe. So, you know, my topic is about exploratory data analysis, which I found extremely important because now we have to deal with a lot of data. And by mean a lot, it's only like half of the true, or maybe even less, because let's say the volume of the data is maybe not that important, because as we know, SQL Server can handle a lot of a big volume. This is really not a case here. The problem is somewhere else, because we need to also be able to deal with data that changes frequently. So we have data in one format, and then it changes at least slightly. So you need to redevelop your solution at least to handle the changes. And that's of course the second thing we can also think about solution that has to integrate many different data sources, like for example SAP, text files, Excel spreadsheets, and so on. And we think yes, it still could be possible. We know that in SQL Server, at least we can use the old-fashioned integration services, or we can use, if we move to cloud, we can develop the process using at least data factory. There are still there are other options as well, but still there is a problem that if we have a classic data warehouse, which looks more or less like this. So classic data warehouse is like a data warehouse where you have dimensions and facts, and everything is very is designed very clearly. It has to be that way because data warehouse is a solution for analytics. It has to be prepared according to documentation, best practices, and so on, which means that if you would like to change a bit this solution, technically speaking, it could be very simple, but has a lot of consequences in terms of how we load the data, how we store it, and maybe how we create then the analytical solution. That requires a lot of time. So building this type of solution means that you have to think about from the hardware perspective. You have to say, okay, I need to think about how much data probably do I have in a year or 2 or 3, and for example, build a virtual machine to handle this size. You can also think how much CPU possibly I need to have every day during the loading process. Then we need to recalculate the fact table and possibly reload analytical solution. And if we don't have analysis services or other type of analytical solution, yeah, then you have to prepare views to connect to reports, which means that it's not easy to think how my solution looks like in a year or 2. So people start thinking about going to the cloud, and of course, buying a virtual machine in the cloud means that I can scale a bit. I have a lot of opportunities and possibilities to scale. So maybe I don't have to think about it this way. But still, I have a lot of questions. For example, how do I store my historical data? My data warehouse need to have like or keep data for 10, 20, 25 years. This is how much you need to store. 25 years is how much. This is the range of time you need to consider when you store medical data in Europe. So it's a long-term solution. So can you design storage for it? So plus solution like on the previous screen means that it is not agile. So adding a new thing requires design, thinking about the consequences, and so on. So we'd rather to do something else, but you know, this is the approach we have in the, let's say, in the data center on premises, which we usually have. means that you have a physical solution in which you can find a compute layer, which means that we have the CPU, we have this, each CPU has to have a memory assigned, plus the storage part when you have all of the disks. So if you really still have it on premises, then you take all the risk that you need to see how is the solution look like in 2 or 3 years, which is kind of tough thing right now. That means it cannot change very much. So the idea is that how can we survive in the world which is changing a lot? We should change our approach because this is how the data looks like now. So it's no longer a beautiful picture with bottles. Each bottle means it's a table, a separate table, which means that we can assign a role to each table. Like this is a customer dimension, this is a sales table, which means it will be a fact table, and so on and so on. In current world, we have to live in a lake of data and try to get the data from this lake, which doesn't look very interesting, but you have to be able to query it very quickly to make sure that your queries can bring answer to analytical question as well. So we are moving towards this solution, and the reason is simple. You can put anything you want in this data lake, in this lake of data, which means that as you can put anything you want, you don't have to think about what is the structure of each type of, let's say, data you put. The data lake contains files, but the file can be in different format from different, from different systems. So it could be extract of any type of data. And as you see here, for example, our case could be to load data from all the green bottles. You can think that this is this is one of the systems that I have, and I need to query it to produce something valuable, something analytical. So the idea is here that we'd like to build build a solution on top of this type of data lake, and this is actually what we do. Because the idea is that on the left-hand side, we have whatever source systems we have. We can attach very quickly another type of system. So if one day you say, I need to integrate, for example, my financial system or my new company, which sends data every day in their format, could be text file, whatever file they have. I can have data factory, which quickly do some preloading to data lake storage, which is the lake from the previous screen, and then we can prepare the analytical solution here. And this is kind of usually you would not use it this way to say I have part of my solution in Databricks, part of my solution in Synapse. You would rather say, because what are those two services? And I can say that most likely you could, in your project, you could choose only one of them and perform all the things you need to create the analytical solution. You can also skip this part as well, because maybe you don't need to create Azure Analysis Services anymore. And if you prepare your solution in a good way, sorry, Teams says something here. Yep, nothing here. Okay, so I'm going back to my drawing. So if you build your solution properly in Synapse or Databricks, then you can connect your data directly to Microsoft Power BI, and this will be the analytical. This will be your goal. This is how you try to build your full, let's say, architectural view of your system. So we try to skip analysis services as much as we can, and try to build everything in Databricks or Synapse. How Databricks and Synapse can work separately, what you can do there. So basically in Databricks, it's like a computational cluster. You can create a lake database, which is going to look into data lake, which you see here, and prepare a solution which basically contains 3 layers of data. So on top of data lake, this is important. On top of data lake, you can create so-called delta solution, and this is something that I'm going to only mention today. So I'm building a delta solution, which means that then during the loading process and data preparation and so on, you are actually building 3 layers. First layer is so-called bronze layer. It's like a bronze medal. In the bronze layer, you have information in the raw format. So as you loaded it from the source system, then you build a silver layer. And in the silver layer, you have information like from, this is my customer, and this is my, for example, sales table, and you build and you join the two information together. So you have something like joint tables or combined tables, and you but the information still it's like we have in the, I would say, in the fact table. Sorry, my mouse jumped back and forth. I have no idea what's going on here, so I try not to use mouse right now. But then finally you have so-called gold layer. And in the gold layer, you build analytical views. And the idea here is that the gold layer is directly then connected to Power BI. Hence, you don't have to create the analytical cube anymore. So everything you can do within your existing solution. And those two things, I mean, this delta layer can be achieved both in Databricks and Synapse Analytics. And I would like to move to Synapse Analytics today, and especially to one part of this process, which means that I'm going to concentrate on so-called exploratory analysis, which is like the part somewhere here. So on the bronze layer, I have data, and I would like to see if my data presents some kind of value. So before I really jump into creating silver layer or gold layer, I'd like to take a look into the data and make sure that I understand how the data looks like. And the reason could be not only to deliver at the end, to deliver analytical solution to Power BI, but could be also a bit different. Because at the end, you can think that from the silver layer, you can also use machine learning. And in Azure, you have a lot of choices how you build your machine learning solution. Could be your own virtual machine. You can do Azure in Azure Databricks. There is machine learning. There are clusters that can do machine learning for you. In Synapse Analytics, you can do machine learning as well. And kind of this thing I'd like to show you today. So how can I make it? And of course, you can create a workspace, Azure Machine Learning workspace, and do it whatever you want. So a lot of options here. And I'm going to concentrate on Synapse Analytics and tell you that Synapse Analytics also allow you to perform tasks that are that uses Spark, that uses Spark engine, exactly like you can do in Databricks. So what do we really have in the Synapse Analytics? So first of all, we can say that we can divide it into two engines basically. So first of all, we have engine which is SQL engine, which is a dedicated pool, which is like a classical data warehouse in which you can build your facts and dimensions. So if you have a project which requires you to build this classic structure, which I have shown you on the first slide, which looks like a bottles, then you can go and build dedicated pool, which contains facts and tables. And you can even build the entire ETL process there as well, if you wish. You will be charged by the number which is called data warehouse units, which means that it gives you the predictable performance. You have 100% of your computational power from the first second the solution is built, and you can scale it up and scale it down as per your needs. However, you have to use automation scripts to do so. It is this dedicated SQL pool is not able to run automatically, scale up and scale down automatically. However, for exploratory analysis, so if I would like just to perform data engineering, I would choose this one, because the serverless SQL pool means that I don't have the guarantee how quickly my solution works, but I can take a look into my data, and having the information from my data, then I can load it to dedicated SQL pool if needed, because maybe I don't have to do this, and I can create kind of lake database here as well. I can use Apache Spark engine and perform the entire solution directly in Apache Spark engine in Synapse, including this exploratory analysis, building bronze layer, building the silver layer, gold layer, and whatever I need, plus the machine learning solution as well. I have integration, so maybe I don't have to use Data Factory, because Synapse has pipelines, which looks like a Data Factory solution, but it's of course only tailored to what you can do in Synapse. So you don't have the full power of Data Factory there, but most likely the operations you need to schedule or orchestrate in ETL solution, that's just right or enough what Synapse pipelines give you. And you have the development, let's say development environment, which is Synapse Studio. So then you can make sure that you can build whatever you want. This will be done through a web page, which I'm going to show you in a second. So yeah, and I think we can jump directly to my task. I would like to give you one more information very quickly, just in a second. But the idea here is that imagine that I have stations on a highway, and the stations has to measure how many cars are driving through it. So there is a highway measurement station, how many cars are driving, how quickly they drive. So we have the speed of them. We can count the cars, and we also measure a parameter which is called occupancy, which means that in percentage we can say what is the load of each of the what is the load on the road. And the idea here is that if I show you this on the web page, on the Google Maps. So if we go to Davis, I think it's Davis in California. Yeah, that's the road. So this is actually the road we have from Sacramento to which is going to the south. If we take a look into the road here, so I try to zoom a little bit here. So maybe, yeah, let's make it here. So the idea is that you can see, I'm not sure whether I am on the correct, because I have to be on not on the CA113, but on the E80. So maybe I will do it somewhere here. Yeah, maybe this is the idea. So I have a data set, and in the data set, I will have information about how the road looks like. And as you see, I have 3 lanes here. So 3 cars can drive in the same way on 3 lanes. So for each lane, I have information: what is the load, so what is the occupancy, count of the cars in some time period, and what is the speed for each of the lane. My data set contains information about 12 lanes, I think, but only 3 will be used. And I have the information from university in Davis. So you can also go to their webpage and download the data, because they make it public as well. Before we jump into the code, I'd like to just to give you one thing here, because using this Delta format, there is an introduction. You know, the idea of big data, which is here presented on the screen, means that we can load any type of data we want. The data can change very frequently and quickly, and we don't care that much about the format and the type of data. And out of the sudden, there is a Delta format introduced, which means that in the big data, we are going to follow the ICID Principia. And you know that the ICID Principia are known from the relational engine. And now it becomes a little bit complex how we make it. The good thing is that the libraries we have, they care about it for us. So we don't have to think about how to create atomicity, how to enforce consistency, isolation, and durability, because this is done internally by the engine. We just need to say that we'd like to use Delta tables there, and that's it. This is what is going to happen. But now let me go to the code and show you. Yeah, I'm going to show you one drawing here, because the idea here is that I know that from the data I have, I would like to take a look and see if I can see some linear relationship. For example, if I have a flow of cars, so I have flow of cars, and how quickly people can drive. So I can imagine it this way, that if I have only 2 or 3 cars, so we can say 1, 2, up to, I don't know, there is like probably 30 cars can go in this road in a single lane in some period of time. Let's say within half a minute, so 1 car per second. So how quickly then can you can drive? So there could be some technical limit, for example, 990 miles per hour, which is like 150 kilometers per hour. And of course, the lowest speed, it could be around 0 if we have a traffic jam. So my idea is that, can I create some kind of linear relationship just by looking into my data, first without introducing the machine learning solution? So that would be my goal here. So the linear regression, which I'd like to introduce, would look like this. And take a look. The more cars I have, then probably they will drive a little bit slower, right? So I can have my data like this, but then I can say that the linear regression, the line should be, technically speaking, look like something like this. And of course, I can have more than one line, because if you have a number of points, the dots you see here, then you can ask, but hey, maybe this line is even better. So the green one you see here, or maybe the blue one like this one, right? So which one is the best solution for you? Because you cannot pick arbitrarily any of them. You have to choose the best one. And the idea of the best one is that we would like to minimize. We would like to minimize the error we introduce. So if we have, so first of all, the equation is like that. We try to predict the y value. So this is the y value, and we have the information from the x value, which means that technically speaking, we will have some a, which is a coefficient, plus another coefficient times the x. So the x and the y values is something we cannot control. This is the data we have. So the linear regression, the idea is that we have to choose the best coefficients, those two. So our solution has to choose those two coefficients the best way, which means that we'd like to minimize an error minimize the error the system has. So it could look like this, that if I have my line like this, and I have 2 points here, so my line is somewhere between them. So the idea is that I would like to minimize the error I have. So the line should be placed like this. So this value, which is the error, should be minimized. So I would like to find the minimum value of the error. So in such solution, when your errors can be both positive and negative, you have to think about that. You cannot just say that I'm going to sum, like this is the error number 1, this is the error number 2. So you just cannot sum the errors like this, because if you do so, then just it could sum up to 0, because one of this will be positive, the other will be negative. So if you are extremely unlikely, they will sum up to 0. So in that case, we'd rather say that the error we have, and the error is what is the value here and what is the prediction here. So we can say that, for example, the prediction value minus the actual value, we have to square it. In that case, we have the always positive value, and then sum up the squares. So we sum up all the squares here, and then we can, for example, perform a square root of them. So we still have a positive value. So this is how the best fit line will be found by our solution. And I have shown already how to make it using the SQL. So I'm going to just briefly show you how you can make it using a SQL approach. So the serverless pool. And then I will show you the same thing, how you can achieve it in using Spark Engine as well. So you know that once you build a Synapse solution, so once you have so-called Synapse workspace, you have to have also your primary data lake attached to it. And this is my data lake in which I have all the my data. So in that case, let's say authentication process is a bit simpler than usual. So I don't have to bother that much on creating, some identity management and so on. So it will be a bit simpler in our case. I start one more time a solution. Yeah, I start one more time Spark Engine, because it already had the timeout during my talk. So I'd like to start it in a second, but first I'd like to show you how can I get into my data. So as you see, I have my lake database, and the lake database is the default one which I have for my serverless pool. And then I have my link services, in which this is the primary one, is the data I have for my from the measurements. So you see my Spark cluster is already been prepared, so we will see it how it looks like. But take a look. My data is here in this part. I have 5 measurement stations. So if I go to this one, for example, I'd like to take a look how my data looks like. And my data is in Parquet format. So I have a lot of data from each measurement in Parquet format. And I can take a look into the data, and I can say, oh, select me, create a SQL script and select, for example, top 100 rows here. And the reason I'm showing it is that now I can show you how you can get data from your data lake. So that's my account, which is here. That's my account name. This is the container I have. And in the flow container, I have my 5 measurement station. And then I have a bunch of files. So if I run it this way, it's going just to take a look into this single file. And this is the query which is generated from the SQL code you can have. So from the SQL code, you can perform this type of analysis just by querying the data lake directly. So you don't have to create any type of structures. You have your data in data lake. I'm not going to load it at all. Just have it there. Of course, we do in a second. We perform the analytics here in Spark because I'd like to show it how this can be done in Spark. So I have created a bunch of files here to show you how you can perform the operation on your own. So first of all, I have information what is in the file. So as I told you, there is a timestamp, so I know when the measurement was done. I have the station number, I have a lane number, and a flow, which means how much cars there were, what is the speed, and what is the occupancy in percent. It should be from 0 to 1, like 0% to 100%, to make sure that then we can design the solution or solution the road, because the idea was how should we rebuild the road to achieve more capacity for it, because that's the one of the main road which is in that area. So I can take a look. I'm going to create a view which says which is called vehicle flow, and the view has pointers to my data lake. As you know how view works, the view does not have anything, it does not store anything, right? It's just like a pointer. And you know that I can take a look into my data just by querying the view, which is in that case, it's going to take a look into the file. So it can take up to a few seconds to load data from the data lake. And as I'm using the so-called built-in pool, I'm not paying for the computational compute layer. I'm just paying for data transfer. And so it is you are paying some $2, $3, maybe $4 per terabyte of data transfer. So you see, I have data taken from my data lake. So then I can take a look into how this solution is built. I can perform a simple select, which will be only from one station. And as you know, this view will be opened. So then the view will query all these catalogs and take data only from this one. This is the one I'm particularly interested in. And then I can build my solution this way that I can create another views with some statistical information. For example, what is the maximum, minimum, what is the average of each parameters, standard deviation, and so on. So I can have another view for it. But then, of course, I can create a linear regression example. And this is actually how to create linear regression without having to create any type of machine learning solution. So I have some coefficients at the end. this select statement will analyze only one station, and it says that I would like to, for example, find a linear relationship between flow of the first lane and, for example, flow on another lane. I can make it. I can say that, okay, maybe I would like to create a relationship on this station between flow and occupancy. And this is something I'd like to take a look right now. But the idea is that then I would like to have those two coefficients, which says A and B, which I already shown you on the screen. And then I have coefficient which says how good the model is correlated. So does the model really explain me the values I see in the data? So hopefully I can run it this way without any problems, and you will see in a second the information from the model. I'm not particularly happy. Where is the completed with error? So maybe I really make some kind of mistake. Let me, I have another views here which are prepared for this solution because I created already. Here I have a view which is called flow occupancy. So maybe I'm going to use this one, which I think should be should work as the previous one. So let me create this view and then query it. So it will be flow and occupancy. The reason I'm jumping back and forth is that I'm going to show how it looks like in Spark, how you can approach the idea here from Spark. Let me take a look what I mess here. I think occupancy casting it to Beacon might be a problem. Those are the coefficients I have in my solution. So A and B can be recalculated if you put the numbers into your model A, B. Then this is how the information is explained. Plus, we have also the correlation here. So the correlation, how the model is aligned. However, let me show how I would do it in my Spark engine. So I created a Spark notebook yesterday, and I would like to show you the entire story, which I should be able to do in 10 minutes. So first of all, take a look. I can load. I do it just to show you how much data I have from those 5 stations. So this is my container, which is in my data lake here. And those are the stations. So I'm saying I'd like to take all stations, data from all stations, and all files which are parquet. So I'm going to load it to a data frame. So let me run it. Hopefully it is it's going to. But you know what I have to do? I have to close this one. I have to stop this session. Yes, and because I have limits on my Spark pool. So let me check if I have something here which uses the Spark pool. So it should be, yeah. If it is not available, executors. Let me take a look into Spark management. So if I go to manage and see my Apache Spark pools here, let's go to the pool, and I should be able to find out what are the sessions in my pool here. So where it is, I should be able to see how many sessions are already running. I don't want to pause it, but configuration workspace, probably I need to be able to find the, how many sessions do we have? This is not this one. Where can I find it? I was able to find it quickly yesterday. and I cannot find it right now. Pipeline runs trigger should be visible somewhere here on the pool. Yeah, current allocations, running applications, active applications, allocated memory. It's not there. So you know what I can do? I can take the pool and in manage, and I can make it a bit bigger. So I can scale it a bit. So if I scale it from small into large, we should have the settings applied one more time, and should be able to make it pretty quickly. It is scaling up. So you know the thing I'm going to do is I'm not going to publish. I'm going to close the on the develop. I'm going to close all my windows here. And I'm going to close the Spark part as well and reopen it one more time. And try to connect. Yeah, I'm already connected to my session. So let's see if this works. Hopefully now my Spark session will start quickly. Sorry for it. Yeah, it's early in the morning, so I'm still not operating in 100% of my ability that I usually do. Yeah, I will explain you what's going to happen in a moment. So first of all, this is just to tell you how can you connect to all your folders and retrieve the Parquet files. What I'm going to do is I'm going to connect particularly to one of my station, which will be called this is the first station 260, and that's the name, and show you what is the schema of the station, what data I have. Then I'm going to show you, and then I'm going to filter the station a bit, the data I have from the station a bit. So I'm going to create another data frame, only with two columns. One will be flow and the second will be speed. And the filter will be that I'm not going to take data when the flow is 0. That means that there are no cars actually. And I'm going to skip data in which the speed is greater than or equal to 100 miles per hour, because I know the data a bit already, and the data looks like this, that there are some outliers, which says that, for example, there is a car which drives 300 miles per hour, which is not possible, because then it's not a car, it's like a plane. So I'm going to remove the data as well and show you what is the schema of the data. We will describe the data frame, so we see what is the minimum, maximum, what is the mean value, what is the standard deviation. So it will be done here. And then I'm going to create a linear regression inside Spark. So I'm creating so-called vector assembler, in which I'm going to say what will be my input column. It will be called flow, and my which will be derived from the flow one, and this will be my output. And then I'm going to do a very simple machine learning process just to see whether I can emulate my data using, if there is a linear regression. So if there are linear dependency between the flow and the speed. So I'm going to split my data into train data set and test data set. And then using PySpark linear regression, from this PySpark ML regression, I'm using linear regression. And I'm saying what is my feature, which is flow, and what I'm going to predict, which is label, which is speed. And I'm going to train the model and find the coefficients. And the coefficients are actually the tool which I have shown you already in the previous screen, so A and B. And then if the model is good enough. So I'm going to show you the errors. So I have loaded my, it says it's ready, so it's still loading the data. So let's give him a try, like a few more seconds. And we should be able to use it very quickly. Oh, the job is in progress, so we should have the data in a moment. We have to start the cluster. it usually takes around 5 minutes at maximum, and the cluster is up and running. So we should have the data. Yeah, you see, 4 minutes, and we have the data. So now the cluster is up and running, so I can do all the fun stuff on it. So this will be the number of data I have in total. In my, it should be like maybe million of rows or something like this. It says 3 million of rows. So you see almost 4 millions of rows I have. But this is from 4 stations. I would like to pick only one of them, which is the first one, which has number 260. So I'm just loading data from this station and count it. Once I have this, I'd like to show you the schema. So you see less than 1 million of rows. And this is the schema I have. So I have time, I have the flow, I have the occupancy and speed. This is for one lane. And then we have a second lane, and so on, up to 8. Previously, I told you 12, but up to 8. But we know already that there will be data only on the first 3 lanes because the road has 3 lanes only. Then what I do is I'm filtering data. So as I told you, only when there is some cars and the cars are driving less than 100 miles per hour, I'm going to cache the filter data frame, which is the best practice, and show you the schema after it. So it should be designed only to have flow and speed. And what are the statistical, let's take a look statistically into it. So what do I have, right? So what is the minimum, maximum, and so on? So I should have this information pretty quickly from my cluster. So take a look. I have, once I filter data out, I have less than 200,000 of data points. And I'm saying that the minimum number of cars is 1, the maximum is 30, and the minimum speed is 0, and the maximum speed is 98 miles per hour. So this is what I have in my data, plus there is some standard deviation. This number will be important, and some other numbers as well. This is the standard deviation, so that's the error we have in data. In terms of the speed, and we would like to see whether our model can make it this good as well. So let's see it. I'm creating so-called vector assembler. So you see I have this is the X, this is the Y. So this is for flow number for 5 cars, probably the speed will be 78, and so on and so on. I'm splitting the data into test and train. And now I'm going to train the model and print you the coefficients. And once the model is trained and I have seen the coefficients here, it says that the first coefficient says intercept, which is 77 miles per hour. And I'm going to show you where it is. And that's the coefficient which has a minus negative value, which is actually a good value because it fits to the model we have here. Because take a look. If we make very quickly one more drawing here, so the intercept is here. So what is the value when my speed is 0? So this is technically when there is 0 or the minimum number of cars. So that's the intercept. And then we have this, the second coefficient was minus 0 something, which means that if you are adding another car, so the slope is negative, which means that you have to slow down. The more car you have, the lower the speed is. So this is what the linear model says to us, and the coefficients are fine with us. So we can, so we understand how they works. And the last thing I'd like to show you here is that what is the error and how good the model is. And there is no surprise that, first of all, the model, the value here is very good because 9.29 is very close to the data we had here. So our model can explain the number here. So it's close to the standard deviation. But then we have a problem because the linear regression, the model can explain only less than 6% of the data. So take a look. I started to show you how can I look into my data and try to perform exploratory analysis? And I fail on this task because my model I created means that I can only explain 6% of data. So what should I do next? And this will be like a homework for you because I'm going to share the script for you with you here. Means that the linear model is not enough. Maybe we should take a look, and if we have the data like on the first screen, so it looks like it was like this one. Sorry, I tried to quickly. I have 1 minute, so I try to tell you what I would do next. Is that if my data looks like this, because probably there is some kind of deviation. So the linear model is just not able to fit to the data properly. And we have to find some kind of polynomial model. But we have to be very careful because the good polynomial model should explain as much data as we can, but should not be that complex. For example, as you see, the line I was drawing right now, because this one is too complex, which means that it is prone to so-called overfitting, which we don't want to have in our data. So our goal will be, or your goal will be, to replace the linear regression to something that can find the polynomial polynomial equation from our data. Yeah, and that's it. This is how we do exploratory analysis. There is one more thing or two more things which could be a bit more complex, like PCA, principal component analysis and feature engineering. But this is basically how I start looking into my data to see some relationship in them. So thank you very much for attending in this in my session. Hopefully you like it. And yeah, I see Andrea is there. So I'd like to introduce
Take your time. This is okay.
No, Andrea, it's early on your side, right? It's also 7 a.m. On your side as well. So because you are 1 hour on the west. Yeah.
I just woke up, so this is more than okay. Plus, you are giving a lot of information, which is going to be very practical for our
I can speak forever on this topic. So I don't want to spend 2, 5, 10 hours on the stage. I think your topic is very, very interesting as well. So the stage is yours right now. So thank you very much for having me here, and have a great event. And now, Andy, do your job. Have fun. Thank you.